Hello everyone and welcome to today's lesson. My name is Furo and in this video we are going to work through a problem involving a spherical ball of charge as you see in here. By the end of this lesson we will have solved all these questions. Let's now read the question. A spherical ball of charge has a radius r and total charge q. Now let's stop here and draw the spherical charge. So this charge is radius r and the charge q. The electric field strength inside the ball is electric field equals to r small to the power of 4 multiplied by electric field max divided by r big to the power of 4. So the question is A. What is electric field max in terms of q and r? We will need to find the electric field max in terms of the total charge q and the radius r of the sphere. And the second part, we will derive an expression for the volume charge density as a function for the radial distance r inside the sphere, inside our sphere. And in the third part, we will be verifying that when we integrate charge density over the entire volume of the sphere, we will obtain the total charge of Q as it is said here. So this problem is a great application of Gauss's law, and it shows how symmetry can simplify our work, and it is really way easier to use Gauss's law than superposition. So let's get started. We will start by drawing a spherical Gaussian surface. Okay, now let's draw it a little bit bigger, okay? Now this is enough. Okay, so this is our spherical Gaussian surface. And it has radius r. It has radius r. Let's start solving the questions. Question 8. It is clear that we are told that the electric field inside the sphere r small is smaller than big R, and it is given by electric field equals to R4 over r to the power of 4 multiplied by E max. And here we are asked to find what is electric field of max in terms of Q and R. So electric field equals to 1 over 4 pi epsilon 0 multiplied by Q R square equals to E max r to the power of 4 over r to the power of 4. This is the formula for finding the electric field. Wait. Just a moment. This is the formula for finding electric field inside the sphere. And we have it here. And if we have two expressions now. If we will search for E max, we will have E max equals to Q over 4 pi epsilon 0 r square. And this is it, guys. This is it. This is the answer. This is our answer now. And it is finished. So let's solve the second part, B. In the second part, we will be also applying the Gauss's law to the surface R smaller than B car. And we will start by applying the Gauss's law. And Gauss's law states that electric field integration of the electric field multiplied by derivation of area equals to, they have direction, equals to Qn inside this our object multiplied by epsilon 0. So now what we will be doing here is we will put the electric field, it is given electric field max are 4 over r to the power of 4. And our area for the sphere is 4 pi r square equals to q n over epsilon 0. And now we need to find qn. We will make qn the subject. It will be, as we have here, q over 4 pi epsilon 0 r square multiplied by epsilon multiplied by r to the power of 4 over r big to the power of 4 multiplied by 4 pi r square. So we will simplify. 4 pi goes by this 4 pi, epsilon goes by this epsilon, and r big. Okay, we will add these ones. So the final answer is q in equals to q r small to the power of 6 over r big to the power of 6. So now, to find Qn, we will be using a thin spherical shell. A thin spherical shell with the r. Let me draw it here once more. This is our sphere. And this is our Gaussian surface. And here we have a small width dr and a small charge dq at a distance r small from the center as shown in the figure. So thus dq dq equals to density multiplied by derivation of volume, and it will be charge density volume multiplied by 4. This is area r square multiplied by dr, which we chose as a small width in the shell. And now we will move with the integration. So integration will be like dq equals to qn equals to density r density r multiplied by 4 by r squared multiplied by dr. You have it in here. So we will now use the qn that we find in the above here. This one we will put inside this equation, and it will be something like qn equals to q multiply r to the power of 6 over big R to the power of 6 equals to derivation derivation pi r 4 pi r squared dr, and it will be density r squared multiplied by dr. And this is, in this part we will put our constants. The constants are easy when doing integration. We can just show them out of the integration. So now taking the position derivative on both sides will be d over dr r r squared times dr will be equal to q 4 pi r squared multiplied by d over dr, and this is our r to the power of 6. You see this, guys? And now it will be pi r squared, so q 4 pi r to the power of 6 r 5. And now the final answer, here density r equals to, this one goes here, and we go to me 3q r cubic over 2 pi r to the power of 6. This is our final answer, guys. We have it here. Now let's move on with the third part. The third part, it is asking from us to verify that when we integrate the volume charge density over the entire volume of a sphere, we will have the total charge Q. So let's start now. The total charge is given by Q equals to expression of R till big R pi R. This is density, guys. Pi R multiplied by D volume. And now D volume let's solve it some other way. This is so simple. Let me show it the other way, which is better. Okay, so this is this paper. So dq is pi to the power of multiplied by d volume. Yes. Now we found that our volume density charge equals to 3q r cubic over 2 pi r 6 multiplied. So the volume is area multiplied by length. So 4 pi r square multiplied by dr. So dq equals to, this one goes to here, and it will be 6q r to the power of 5 over r to the power of 6 multiplied by dr. Q equals to the Q derivation we'll use 6 Q over r to the power of 6 from 0 to r5 dr. This will give us Q equals to 6Q over r to the power of 6 multiplied by r to the power of 6 over 6. So this goes by this and this one goes with this. So what will be left is only Q. And we have it here, our final answer. It is Q equals to Q. And finished, guys. We solved the third part as well. So these steps show how powerful Gauss's law is when combined with symmetry. Like, we cannot use Gauss's law without using the symmetry, of course. By differentiating the enclosed charge, we obtain the local charge density, and by integrating, as we did in the third part, that density, we can confirm the overall charge distribution. So thank you for watching this lesson. I hope this detailed explanation helped you guys understand how to approach problems involving spherical charge distributions. If you have any questions, please feel free to leave a comment or ask during our next session. Happy studying and see you all next time. Thank you.